Hey, good morning. This is the solution to the journal bearing question, where you have an oil flowing through a two different plates. One is moving, while the other one is stationary. Now, looking at this, when a fluid is moving through a plate, the velocity at the stationary plate is equal to the velocity of the plate. Since the plate is not moving, definitely the velocity will be zero at that point. But as it's going up, the velocity is increasing. Velocity is increasing. That's why you see this arrow is increasing as the height increases. So we only have, and since this profile is two-dimensional, we have x-axis and y-axis. We will have velocity on y-axis, that's v, and then velocity on x-axis, that's u. So since this flow is a laminar flow like this, that means the velocity on x-axis, and it's not like this. This is a turbulent flow. Looking at this flow now, we have both velocity on x-axis and y-axis. But in this case, we only have velocity on x-axis, that is the speed of the moving fluid along x-axis, which is the same thing as u, while the speed on the x-axis here is equal to 0, because it's not turbulence, it's a laminar fluid. The fluid is moving like this in a straight pattern. It's not moving like the motion of a sea or ocean. So we only have our u of y and v to be equal to 0. So that's why you see from the question, you see u of y, while the velocity of the plate, that's the moving plate, is 12 meters per second. So since we have our v now, velocity on y-axis to be equal to 0, definitely the v dx is equal to 0 and the v dy is equal to 0. Also, we have our u, which is the velocity on x-axis. So if you differentiate it, the u dx, the velocity is not changing on the x-axis. That is, the velocity of the fluid at this point A is equal to the velocity at this end here. So the u dx is equal to 0 and the u dy is not equal to 0, because the velocity is always changing. The velocity is changing along the y-axis. So having gotten these four parameters now, so we'll go to the momentum equation. So momentum equation says that rho into bracket u dv dx plus u dv du dy okay is equal to mu partial square u over partial y square plus partial square v over partial s square. Now, from what we have gotten so far, our dv dx, what's our dv dx? 0. What's our u?
0.
Our u, we have a function for u. So this one is not equal to, but the u dy is what?
0. That should be v.
Yeah, right?
Yes. It should be v du dy.
Okay, yeah. V. So this is v. Why this one is u? U dv dx. Why this one is v du dx? But because v is 0, so this part turns to 0. Then when we come to this side, the the square u dy square is not equal to 0 because of this. So, but the square v over the s square, that is, when you differentiate this function, this one now, you still get 0 again. When you differentiate this velocity 2 times, you are still going to get 0. So this one automatically turns to 0. So we are left with everything at this part is 0, And
that last parameter,
yes,
we use pressure the other time.
no, that one is for heat dissipation. Okay, there is pressure there.
No. It's
Minus
partial pressure.
dV dx. So the pressure too is not changing on x-axis. So this one is also 0. So we are left with 0 is equal to mu, that's the viscosity, the square u over the y square. So that's what we got from the momentum equation. Now, since this equation is only one dimensional, we can change it to total differential. So this one will give us mu the square u over the s square is equal to what? 0. So we can now integrate this equation now. So we are looking at this, we can divide both sides by mu. So we have the square u over, this is the y, over the y square equal to 0. So let's integrate the function.
So my integrate is 11.
We have integral the square u over the y square is equal to integral of the 0 dy. If you integrate this function, you have the u dy is equal to what? C1. You integrate again, integral the u dy, integral C1 dy. This will give us u of y is equal to C1y plus C. C2 rather. Thank you. So that is the first aspect of the equation. And now we need to substitute for our boundary condition. So from the boundary condition, the velocity at the surface of the lower plate, that is the stationary plate, u of 0, that is when y is 0 now, our velocity there is 0. Then u at the length, that is when y is equal to L, that is at the moving plate, is what? V, which is 12 meters per second. So let's represent it V now. So we have u of 0 is equal to, we substitute 0 wherever we see y. So that will give us C1 into 0 plus C2. So everything is equal to what? 0 because of this. So we have 0 is equal to C2. So our C2 is equal to 0. So we plug this value into this function here. So we have u of y is equal to C1y plus 0. So there's no need of writing it. So we apply the second boundary condition. Second boundary condition says u of L is equal to V. So that will give us u of L is equal to C1 V. We substitute L instead of y now. Are we together? So we now equate it to V. So definitely C1 becomes V all over L. So go and substitute this one now into this equation. So we have u of y is equal to V over L y. So this is the velocity equation for the flow of the fluid in the internal bearing. So this is question A1. We have just solved question A1. Now we go to the second part of the question, which is the heat dissipation. So the formula for heat dissipation is given as Formula for it is given as rho Cp, that's specific capacity, multiplied by the velocity u dt dx plus v dt dy is equal to k into bracket t d square t over dx square plus d square t over dy square plus mu into bracket is actually mu phi. So where phi is another function on its own, which is equal to 2 into bracket du dy square plus dv dx square plus bracket du dx plus dv dy, everything square. But we don't need all this one, we only need this first part, because everything will be equal to 0. So that was why I omitted it the first time that I was solving it. So you don't need it. So let me rewrite the equation.
You don't need which one first part.
For this heat dissipation equation, we only need, this is the only thing we need here.
Please give us only two.
That's what I want to rewrite. We'll see the video. So we only need rho Cp into u dt dy plus v t dx equal to k into the square t over the y square, because the temperature is only changing along y direction, plus du dy square.
Mu is missing there.
Okay, mu. So from this place, our u, our dt dy, our dt dx is 0 and velocity is also 0. So all this one is equal to 0. So you have the 0 is equal to k into the square t over the y square plus mu du dy square. So when you want to do this second one, this is what you need, this part alone. Forget about this one. You understand? Forget about this one. Just write this one. This equation is this. K square t over dy square plus mu du dy square is equal to 0. That's the equation we need. So now we are going to integrate this equation now twice to get the temperature function. So from here we can say k d square t over dy square is equal to minus